my talk on Chapter Scheduler and my CPAN handles Caldrin. Chapter is a test automation system that we wrote for our own purpose. And last year we got the permission of our bosses to make it open source. So now you find it on CPAN and on GitHub. And the main purpose of this talk is to make Chapter known to the world. Because we not only search for people who use it, but also search for people who want to increase developer force. I think the best way to do this is to show the coolest part of the tool, and hopefully people will join in and have fun developing. Just to tell you, I was hoping to show you lots and lots of code, but due to timing restrictions, there will be little code calls. If you're interested to see more, just come to me later and I'll show you. Okay, what's this all about? I work for AMD, a processor company, in a department called the Operating System Resource Center. Our department is responsible for making sure that AMD processors are well supported in modern operating systems, especially Linux. This also includes virtualization features like Zen and KVM. That's what our developers do, and I'm part of the team that does software testing. We try to test not only what our developers did, but also what the world did to this project. For example, if a new patch comes into kernel, we make sure that it doesn't break anything on the machines. The issue we have for this testing is, first, we always have too few machines, especially those with upcoming processors, which will be in the market in like half year, even more. We only have very, very raw engineered examples of them. Never enough to test every single test. The other thing is we always have too many use cases. For example, take Zen, virtualization software. Issues with this can occur with very specific combinations of guests, for example. So there are each matrix of guest combinations with Windows, with SLAS, with RHEL, to test all these to make sure it doesn't ever break. For these testing, you need automation and a strong scheduler to distribute the use cases onto the machines. We had some initial goals before we started implementation of our scheduler. Because first, we only were able to put test requests onto machines in the first in, first out manner. Our tests are organized in use cases of different components. We test Zen unstable, we test different versions of the kernel, and of course, testing in an unstable tree of some project needs more bandwidth than testing a stable tree, because a stable tree doesn't change so often. So we have use cases of different bandwidths. Our developers need exclusive access to the test machines. They work on weekdays from 12 to whatever, and on weekends we have access to test on these machines. So there has to be some way to give them access. We want even distribution of use cases onto the available machines. Doesn't it make sense to test kernel on one and Zen on the other? We don't find issues that are machine dependent. Furthermore, sometimes you have hardware requirements for your tests. To test a multi-CPU patch on a single CPU machine obviously doesn't make so much sense. Or especially we are informed of an issue in Zen. The first thing our developers test is, does this break on an AMD machine? The second thing they test is, does this break on Intel? And if it does break on Intel, they relax a very bit because it doesn't reduce our amount of processor sold. So you have to tell the scheduler this test request has to run on, well, either you think of naming a machine specifically, which is what our developers do most of the time, but sometimes they also say, well, something with Intel, don't care what. We need to finalize the test definition as late as possible. Imagine the Zen matrix I told about later, earlier. When you put like 1,000 tests in a database, obviously the last one tested will be days apart from the first one. When you say, well, specifically this build of Zen will be outdated when the last one is being scheduled. So we make sure that the test description is finalized as late as possible when the test request is actually scheduled. And lately, the scheduler also has to have a good test coverage to make sure it doesn't break anything. This is the way the scheduler actually looks like. We have the use cases which are organized into queues. For queues of test requests, 3 queues in our example, and there is a core algorithm, which in our case is weighted fair queuing. This algorithm chooses a queue. Then every test request in this queue is matched against the set of 3 hosts. We check whether the alpha requirements match features of the host. No match is found, and the next queue, until if you do found a match, then at this point the test request is finalized and returned to the call. Sorry? No, that's just for giving a picture. That's not really a rule. Okay, the core algorithm, the weighted fair queuing in our case, the goal for it has to be fast. We don't have too much calculation at this point. It has to be fair. No use case should have a starve. Every use case has to be tested eventually. And it has to be bandwidth, because I told you different use cases are what it does, it gets a list of queues that haven't already been checked and returns the next queue. It is pluggable because we made it a role for the size who's declare scheduler. And so we can use a dummy scheduler for testing. This dummy scheduler is very easy predictable. We can ask the scheduler 100 times what would be the next test run, next test request, and check whether this is what we expected. In live mode, we use an algorithm which is called weighted fair queuing. I mentioned the easiest way to implement a scheduler which fulfills all the goals that I mentioned would be giving first queue all of its share. Somebody have a bandwidth of 1,000 and test 1,000 times with this queue. Then the next queue, and the next queue, and the next queue. And then with an infinity time, it would be fair. But in a short time frame, it's not so fair, because the second queue is tested for the first time after 1,000 test requests are already scheduled. Weighted fair queuing is much more clever. It calculates the fair share of every queue, which is how often did it run and what bandwidth is assigned to it. Then it calculates what would be this fair share if we run the queue once more. And the queue with the lowest fair share plus 1 is chosen. I have more details on this if we have time later, but if you're interested, I'll show you those slides. Well, and the matching part. Matching hosts is obviously the most important because, as I told you, our developers single host name most of the time. Requesting a host means this test request only runs on this host. You can give multiple if you want a set of hosts. You can bind a host to a queue. This means the host will only accept test requests from this queue, and therefore this use case. This is the way we give exclusive access to the developers. Every developer can open his own queue, or her own queue in this case, put his own test requests into this queue over the week, and on the weekend he releases the binding, and so we have access for all test requests on this host. Therefore, raw machines are used quite well. Quite interesting feature matching. You can give a feature, as you see here, request a feature, memory more than 4 gig. This is Perl code. You can put any Perl in it. Talk about it later. The way we implement this is we have a database which contains every feature of every host we use. We use SafePM to protect against misuse, because someone may request a feature like system RM star, not the feature I want to deliver. Yeah, you can get multiple features I want to mention. Okay, an example of how we implemented this. This is all in the schema, because the scheduler can't inherit from DBIC. It's currently not possible to inherit with who's.x declare from a DBIC schema. I talked about this last year. If you're interested, I'll tell you more. So it's in the schema, and the first thing we do is we get all the features of all hosts, every feature that's in the database. Then we put the features as functions into a global variable called functions. And then we create the subs, every feature key as a sub, which returns the feature value. So this is evil, this is created. I do know there's a security issue with this, because if there's something malicious in a database, well, I don't know what it may have, but probably a bad thing. I think it's not so much of a problem because, first of all, we have control over the database. There's no one else who has access to it. And second, we only want to be sure against accidental misuse, because our developers don't have so much of an interest to break anything. In this case, they had to test manually. This is the actual matching function, which is also in the schema of the test request. It first checks whether the free host, which is given, to match, or if the queue bindings of this host allow me to test on it anyhow. Then we make a conformant of DBIx with the core functions and the function we created already, and check whether they match. First match we find, we return. If not, we don't return anything. A very interesting issue we had with all this was something we call black and white networks. The problem is high machine utilization and good use case distribution conflict with each other. Because if we have a machine that didn't have its fair share of one use case, it has to wait for this use case to be scheduled. With bound hosts, this is even worse. What happens is that the first queue that it asks when a new host becomes free doesn't have any test request for this host. So the second queue jumps in. Now the run count of the second queue is increased. Therefore, it doesn't have any fair share left to compete with the first queue for rare machines. We solved this by not punishing the second queue for jumping in. Actually, it's quite hard to find out whether a queue jumped in, because imagine the first queue was empty, and that's the reason why it was unable to give out a test request. In this case, you do want to punish the second queue, because otherwise the run count of any queue would not change ever. Again, if you're interested in more details, ask me. How are we in time? Little bit of what I thought. This interesting issue is putting scenario in. Scenario is when multiple test runs belong together. Easy example, you have a client-server test. Most of these test runs will be put into the same queue because they belong to the same use case. When the first test request is scheduled, obviously it should not wait too long for its peers. If it's a low bandwidth queue, then you have to wait far too long. So the solution is we put all elements of a scenario into a special priority queue as soon as the first one is scheduled. You want to ask something?
No, I'm just...
Looks like it. Okay. And this priority queue bypasses the scheduling at all. It's always checked first for matches. And for as soon as the hosts become free, hosts become available for the second, the third, or how many ever test requests in this scenario, it will match. And the first one doesn't have to wait. Furthermore, the scenarios can also sync with each other to make sure they start at the same time, but it's not in the scope of the schedule. As I said, I want to encourage you to join the development forum because the scheduler is not yet finished. The first thing is it has unsatisfying speed with like 30 test machines and 40 use cases. We sometimes need up to 10 seconds to find the next match, which is too much. We started with auscarving the precondition producer, which is a part you call the robot, which finalizes the test request. It doesn't help enough. We think the best part to make the scheduler faster is to pre-calculate values. For example, when a new test request comes in, you could calculate on which host does this fit. Use this for the scheduler instead of letting the scheduler calculate it itself. Or whenever a scheduler finds out this test request doesn't match the free host I'm currently checking, it may remember it, and when the test request isn't fitted, well, maybe we can find this point faster next time. Also, we want to carve out the scheduler as a separate tool. Currently, it's deeply in Tapper, so part of Tapper. But maybe someone is interested in having a scheduler for other tasks. So putting it as a new API and a separate tool would be interesting. Finally, this is how you find us. We are on GitHub, search for AMD. We are on CPAN. There is a mailing list, which currently doesn't have too much traffic. There's an introduction site about the developers' web pages, and we have an IRC channel, which also doesn't have too much traffic yet. Thank you for your attention, and now for questions.
So these public resources you have, do you actually publish the figures of your test runs, or do you like to keep them private?
We do not yet, but we want to. We have Tapper has a web GUI, but this web server is only available internally yet. That's mainly because we didn't separate those parts which are open and those parts which are in the A. I don't have a time frame.
Sure.
But if you're interested, no. I don't have a time frame. Just wanted to refer to my boss, but he knows that I came up with a good idea. Okay, other questions? Yeah, please.
The feature database of your testing servers, is that automated for creation of the database and updating it?
Unfortunately, no, it's not.
How is that represented in the online resources, the CPAN online, things like that? Is it just instructions on how that database is set up?
We set up this database manually. We do have resources documentation about it, and it tell you how you put information in the database. Because it's actually quite easy. It depends on what features you want to check. You have one table which contains every feature of every host. This feature, this database has a host ID, which refers to a host table, a key, in our case memory, and a location. We also have vendor and numbers of CPU like that, but it's not automated. Main part is because you don't know what anyone wants to test outside. For us, this is the important part. For other people, others may think. Other questions? Yeah.
Are the tests just standard code tests?
It's not code tests, it's system tests. LTP, for example, is testing project. Or benchmarks, third bench and a bench. But I do know of one guy who wants to use Tapper for testing Go, actually for benchmarking Go. I think there also is a talk about this tomorrow. Look out for Steffen Schwieger. We know about this. Any more questions? Yeah, please.
Does it record the history of the test execution, or is that something that we have to do yourself as well?
Yeah, it does. It puts every test request and every test result into a separate database. And we do a little analysis about over all the data we get. So, for example, we make meta reports. We check how pass to fail ratio of one use case changed over time and give this out. There are also plans on implementing more analysis. For example, putting rank expressions over reports that come with this tab. So it's quite easy to analyze this, but it's not. Anything else? Oh yeah, please.
Given that the web GUI isn't open source yet, what do you get if you're using Kafka restricted to CPAN? You get just the DBIx, or is there like a web part?
Okay.
What's the output for this?
You have to write your own tests. It doesn't come with tests. These tests send tab to a server. And the server is responsible for putting the tab into a database.
Can you please get problems for the initializing measures like speeds? Have you investigated anything existing on SQL already?
We have put NYT proof on it, but didn't give too much information. Well, there is no single point of single point where we waste our time. There's much DBIc and we have much database queries. So it also takes time. And then again, it's also not optimized ever. For example, checking host bindings and whether host matches means we go to I think 3 loops of M3. I see it's end. No, it's this way it's end. I thank for your attention.